Well, hello everyone. Thanks so much for joining us. We've got about twice as many people signed up, and so there's going to be some people trickling in, but out of respect for the people who had the courtesy of showing up on time, let's get this underway. My name is Dave Biggs. I'm a board member here at the Gibsons Public Market, and I also volunteer with the Blue Act Marine Society. Got it. We just had a renaming process, so I've got the old name stuck in my head. Energy is an issue that has been drummed into my head for ever since I can remember. In the 1970s, my father ran the energy conservation and solar energy program for the country. And if I left a light on, I heard about it for days. And so when my wife and I purchased a bed and breakfast that used a ton of electricity, I heard it from my father every day. And it wasn't until Liam came and installed solar panels all over the roof that he actually said, "Good lad." So finally we're at net zero and I can breathe again. And I'm just thrilled about this topic. That has motivated me to just keep going. Where else can we save? What else can we do? Where can we go from an energy perspective? What about water? And it kind of has steamrolled for me. And so that, I think, is a wonderful way that it's happening for a lot of people around the coast. We have a really engaged community on environmental issues, and we have great resources. And this panel today is just exemplary. So I'm going to give the majority of the time to them and then the rest of the time to you. So if you have any questions, we're going to have several breaks throughout today where we're going to take your questions. We're going to start with Dr. Ross Gordon. He is the lead and go-to energy advisor on the Sunshine Coast, and his outfit is called ARG Energy. He's going to begin. He's going to then pass it over to Brad Jennings. He is partner and president of Summerhill Fine Homes. His work is actually building these homes and making them as energy efficient as possible. Then we've got Jerry Pajot, and he is an expert on home energy efficiency and a board member of the Sunshine Coast Community Solar Energy Association. So another great resource. And finally, Liam Bonsar, who was the installer for our solar panels. He is the owner and master and Red Seal electrician with Newbon Canada, and he's gonna finish off. So we're gonna cover a wide range of issues on what you can do from an energy perspective, how you can evaluate what to do first, what the steps are to be taken, and then a little bit more roll up your sleeves. How do we actually get this done? What does it look like when it's into your home? So I'm going to pass it over now to Dr. Ross Gordon. Thank you very much.
Of course, it's important to just take a moment to appreciate the opportunity we have to be here on this land. So, good evening. I'm really excited to contribute to this climate action series. I live in Sechelt, and I work on the coast as a Natural Resources Canada licensed energy advisor, working with residential homes. In a parallel universe, I have academic credentials in environmental anthropology, and I've taught courses at UBCO like political ecology, living in the Anthropocene, culture and nature, and these sorts of things. My training and research area has been how people understand and relate to their ecological environment. But now I've become very intrigued with questions about people's relationship with their indoor environment. Why is that? It's because we're experiencing dramatic changes both in the outdoor climate and also changes in how we build and design homes to create more distinction between the indoor and the outdoor, which means this is changing how we think about our indoor climate, and we're going to talk about a few different aspects of that tonight. So I'm going to run through, it's about 12 or 13 minutes, I'm going to run through a bit of a talk, the microphones, run through the talk, and then there's lots of times for questions, because I'd like to keep the flow happening, and then we'll come back, and so if you just hold your questions to the end, happy to engage. So homes are being made much more airtight for energy efficiency, and as mentioned, more than ever, our homes are sanctuaries from changing climate outside. So let's start off by thinking about the distinction between how do we feel in our homes and how do we feel about our home. How do we feel in our home relates to the building technologies. This is a really important distinction, because when you're trying to make decisions about upgrading, if there's so many different pieces to those decisions, and I think it's really helpful to distinguish between how we feel about the home and actually how we feel in it. And we'll drill into this a little bit more as we go along, because this really relates to experiences, and everybody has some different ideas about that. So just for fun, if you share a home with someone who has different ideas than you do about what home comfort means, raise your hand, please.
You're bad.
Now, please, I did anticipate that. Please raise your hand if you kept it down last time because you did not want to start a fight over home comfort beliefs. So I think it makes the point. There's two different sets of ideas we need to think about. One is how we feel about it and how everybody else in the home feels about it, and how the home actually functions. So the point here isn't to start fights, but help you isolate the technology questions as you go through down the path of making changes from the experience questions for the purpose of planning. So the first step in planning energy upgrades for an existing or new home is to determine how you want to experience the home before you dive into the technology and the cost issues. Otherwise it becomes just a big ball of string and you don't know where to start and where to stop. That way we can start to not get overwhelmed and start to make a plan to choose the technologies to improve the energy efficiency of your home, save money, and improve home comfort. The energy plan for a new or an existing home is based on building an energy model of the home's exterior envelope, the mechanical equipment for heating and cooling, and ventilation. This is actually what I do as an energy advisor, is break all those things apart. So let's start with some of the basics of energy modeling. So just a little bit of physics, we'll keep it light. When we start to model a home, we're evaluating all the components of the home associated with energy use and flow. Heat gain and heat loss is a lot more complicated in a home than most people realize, because there's 3 different mechanisms of heat flow in buildings, always in play in many different ways. So they are conduction or heat transfer, convection or movement of air, and radiation of heat from the sun or a mechanical heat source. So in energy modeling and planning, we must isolate the technological processes from our experiences of them. So just for fun, reach down to maybe the little bar on your chair and feel the metal, and just feel how warm or cold that is. Now take the same hand, if you don't mind, and just reach down and touch the wood on the floor. What's the difference in temperature? Did one feel colder than the other?
Floor's warmer.
Yeah, floor's
Is the floor really warmer? Or do we feel differently because we don't feel temperature? We feel change in temperature. So the metal conducts the heat away from our body very quickly, because metal conducts heat faster than the wood does. So there actually isn't the that's a really, it's simple, but it's complicated because we think of feeling temperature, but we're actually feeling temperature change when we notice temperature. Okay, so that's basically the hard physics lecture for tonight. But just remember those three different conduction, convection, radiation. All of those three elements are in play in every house, and every component of the house envelope, the walls, the ceilings, the floors, are all, these things are going on to some degree or another with most of the different components. That's why it's important to think, we're going to talk a lot tonight, and the other panelists as well, about a house as a system, because there's many different components that interact and are doing different things at different times. So for heat conduction alone, each element of your house performs differently. When I actually do an energy evaluation, I'm estimating the current total heat gain and loss performance of each house element and interactions with other elements. Then we can start to identify the potential performance of possible upgrades. There are technology change projections. These projections help produce upgrade estimates. The idea being, if we figure out what each element is doing in terms of heat gain or heat loss, depending on the season, and we think about changing one thing, we can start to understand how it's affecting other things. It's a system. A lot of times people come to me and say, I want to get this, or I want to do that. And my first step is always to say, okay, let's get a plan here and think about what the priorities are and how each change is going to affect other changes. That's why the planning is important. So the goal is to be able to compare the technology performance upgrades then with the home comfort benefits and cost estimates to make a plan. So breaking out the technologies and then thinking about how you want to feel in your home helps us make good decisions. So indoor climate control goes beyond home comfort too. It's also a health issue. Many of us spend up to 18 hours a day in our homes, and as we make our homes more energy efficient, the interior living spaces become more discrete and unique to the home's location, structure, and mechanical systems. According to lung health researchers at SFU, the best public health policy advice for wildfire smoke or extreme heat is to get people to stay inside their homes. But if the homes aren't sufficiently airtight, insulated and cooled, and ventilated with filtered air, this is not a solution. The key point is that one of the key points I want to make tonight is that indoor climate control is a homeowner's responsibility. Governments can offer incentives, but homeowners need to take action to make their homes resilient to extreme climate events of heat, cold and storms, smoke, etc., to ensure their health and comfort. This is our reality now and in the future. So why are modern homes discrete climate zones now? As I mentioned, this is really a relatively recent change. When people heated with open fireplaces or coal furnaces, homes were drafty buildings with air leaks everywhere. Combustion heat warmed up the airspace near a flame, but sent most of the heat up the chimney. Replacement cold air entered through cracks and holes in the building. This is what's called an exhaust-only ventilation system, and not very efficient, given the amount of wasted heat up the chimney, and not very comfortable near the walls where cold air is entering. So for cooling, in that system, you just open the windows, which doesn't always work now. A more recent house design with just kitchen and bathroom fans for ventilation. So many of our houses, the only exhaust of air out of the house is when you actually physically turn a fan on, meaning a kitchen or bathroom fan. So that's still an exhaust-only system, because the ventilation in heating season is sending, the weakness of it is in heating season, doing that is sending warm air out of the house and still finding cold air replacement to come in through the cracks. So this exhaust-only air movement creates what's called negative pressure in the home, drawing other air in from outside. So exhaust-only systems also assume a clean outside air supply. The exhaust also may not remove all the fuel-burning residues, particulates, and gases that are made in the home from cooking or coming off other substances. So over the years, as gas or electric furnaces and baseboard heating replaced coal and wood devices for home space heating, smaller percentages of unused heat were wasted, less air was drawn into the home, reducing drafts and improving air distribution. Our expectations of home comfort have come up as well. So the house envelope is an important term. You'll hear a lot tonight. So basically that's the defined separation between the indoor and outdoor climate, all the components of the home that form those barriers. So ceilings, walls, foundations, etc. All of those reduce conduction heat loss, and better quality windows, of course, are part of that and will also reduce heat loss in winter and heat gain in summer. The trick is in the connections between the components. When you're building a house, we're going to hear from an expert builder on making energy efficient homes, and I'm sure Brad's going to be talking to you about the seams of the house, how you stitch the windows to the walls and the roof to the walls, all these elements. This is often where the air leaks happen, and we'll talk more about that. So good connections are critical to resist the incoming air. Now, another important idea I just want to present to you here tonight, because it tends to be a little bit confusing for people not familiar with it. Today, by building code in BC, and it's a recent change, the house envelope in new build homes is required to include a balanced mechanical ventilation system, often known as a HRV or ERV, heat recovery ventilator or energy recovery ventilator. What this is a box with a lot of little metal tubes that cross over each other. And there's 4 pipes. One pipe draws air. There's a little fan that runs. Doesn't use much electricity. One of the pipes draws air in from outside, pushes it through tiny little metal tubes, metal conducts, as we talked about earlier, and then moves into the house. The outgoing air, which is warm in heating season, crosses the path of the incoming air, so you get about a 75% recovery rate with the air change system. So you get fresh air in the house and stale air being exhausted all the time on a steady state. So this is now where, as I mentioned, new homes are required, and this changes from an exhaust-only system to actually a managed ventilation system, because it's ongoing. The key difference between, you see these terms ERV and HRV, ERVs adjust for humidity as well to help balance that out on the way in and out. So there's a lot of stuff on this graph here, on this little chart here, but the point is to show how heating homes has changed. 40 years ago, houses were leaky, energy was cheap, and occupant loads were less significant. So way back here, most of the energy being used in a house was going to heat space heating, and a lot of it was just going up the chimney, literally, or out the windows. Modern homes use a lot less energy for space heating by using more efficient heating systems such as heat pumps. In contrast, the occupant load, as you'll see on the far chart over there, I'll start it up here and it'll gradually come to me. The occupant load actually has now become a much higher concentration of the percentage of energy used. Think of all the devices we have now compared to 40 years ago. But the focus here is just to show that heat loss decreases with more energy efficient construction methods, and that reduces random airflow through the envelope. Air leak testing I'm going to speak to a little bit here, and I think Brad's going to pick up on it in a few minutes as well. When I do a home evaluation, whether it's for a new home to test it or for a home that's being evaluated for efficiency, I do something called an air tightness test, where I put a fan on the door and it draws air out of the house, so it sort of speeds up the depressurization process to simulate a 30-kilometer wind hitting the house from every direction. And then this is a standardized testing system nationwide, and homes then are rated to a certain amount of air changes per hour, which is basically the speed of replacement as the air is drawn out of the house, and also the total leakage area, meaning if you take all the cracks and holes in the house and put them into one thing, is it a basketball or a yoga ball or a baseball? So those are two terms that you'll see, and there's a standard grade. The actual internal air volume of the house has to be calculated as well to factor, and air temperature differences inside and out. There's a few other factors that go in. So again, this is a part of the idea of a house as a system, because now we're measuring the effectiveness of all of the different elements of the house envelope combined, and also how well they've been stitched together. So how well were in the actual construction process, how many little gaps were left behind through construction techniques. Okay, so we control our indoor climate by making decisions about the system components we choose, how we use them, and how each component affects other components. For example, if we increase insulation levels or fix air leaks, then we can buy a smaller heat pump that will reduce energy costs and be more efficient. Everything's interconnected. So once we see that a home is a system, the plan allows us to anticipate outcomes when we make changes to the system. When I work as an energy advisor, I evaluate existing homes to determine current energy model system components and then provide planning options for different combinations. This is the path to make good decisions to design and control the home's indoor climate. So here I'm stressing the technology aspects to come back to the first slide, and then pairing that with what your idea of home comfort is and what your goals are, and then you can start to put those pieces together. Now, I also work with new home builders to design homes right from the plans. So we build an energy model from the plans and the projections of what kind of mechanical systems that are going to go in to meet current building codes. And in BC, you'll hear more about this later, but there's something called STEP code, which is a standardized level, which is gradually being advanced every few years, that houses need to be built to a certain degree of energy efficiency. So that has to start right at the design stage to achieve. So in terms of incentives and loans and rebates and all that sort of stuff, that's geared for next week's talk. This is a two-part series. There's just so much to cover. We had to break it all up, but we can dig into that more next time. And I just want to stress that by making good planning decisions, when we start thinking about upgrades, we can reduce our home's emissions, we can control our indoor climate for better comfort and health, and we can reduce operating costs and our emissions footprint. So with a plan, we can change how we feel in our homes and how we feel about our homes. Now, there's one caveat I want to put in. I don't do couples counseling for what the right temperature is at night to sleep. That's not in my toolbox. So, and that's next week. We'll dive into that. So I've got a few more minutes with my time allotted, and I'm happy to open up for any questions. And we can go back to any slides if there was anything anybody wanted to review. Well, either I did a really good job or I put everybody to sleep. All right. Well, that's great. So, and we'll have more time for questions at the end, so if anything comes up. So thank you very much. And I will pass the baton to Brett.
So thanks, Ross, for leading us here, and thanks, Dave, for inviting me to the panel. For Dave's introduction, I'm a builder here on the Sunshine Coast. I grew up on the coast and became a residential builder here in the early 90s. So have seen a lot of changes in our industry since then. In 2010, after sort of taking a hiatus from building and being away on a sailing trip, I came back and got back to work and wanted to, sort of lean into the green building that was going on. So joined the Canadian Green Building Council, and I've been since then been part of some LEED building programs and passive house projects and here on the Sunshine Coast, and most recently built my own Step Code 5 house, which turned out to be a really good learning opportunity as a builder. And so I'm going to share that with you as sort of our case study, and share my experience with that, and hopefully you can take something out of it. If you're not building a new house, it doesn't really matter. There's probably things that might be meaningful for you still. So I'm getting used to this, how this works. Okay, so yeah, as mentioned, since being part of the Canadian Green Building Council, we completed a house just up here on the bluff to a LEED standard, and LEED is just a green rating program, and it's sort of a very integrated program, and I quite like it. It considers the building of the house or building, and considers its linkages to transportation, and it's a very sort of multifaceted rating program that was fairly popular, but kind of a little bit cumbersome too, so it didn't really catch on in the residential building. Alongside that was Passive House, and Passive House has been a sort of a big contributor to the education and developing the technologies in the industry, and it's a rating program based out of Germany that gets the house to a very, very low energy use, and it's basically sort of set the standard as far as energy efficiency in homes and new homes, and since then the government, I guess, saw what was going on with passive houses, and saw that there was an opportunity to make our housing stock much better, much more energy efficient, and so they took on climate commitments internationally, and said if we're gonna make these commitments, we're gonna have to make our buildings better, and that's going to mean sort of getting to passive house standards, and setting the target for that for 2032, and approaching it, not just dumping it on us as builders, saying that we'll take steps to get there, and we have target points being to make improvements to the code. But by 2032, all houses are meant to be sort of net zero ready is what the step code goal is. So basically, the envelope of the house is going to be very robust, and the energy use is going to be very low. And with the addition of some on-site renewables, the idea is that the houses can be net zero, and so in other words, not need sort of any additional electricity. And so, yeah, just speaking to the step code targets, by 2022, which is what we're building to now, we're 20% sort of more efficient than what the baseline house would be, which is the 2018 BC Building Code standard, and by 2027 we get 40% better, and as mentioned, 80% better than the 2018 baseline house by 2032. So Ross kind of talked about this a little bit, but the houses as a system, and the three or the two sort of major systems in the house or create the energy efficiency is the thermal envelope and the mechanical system. And both these are by spec and in the design of the house. So when you're working with your builder or with your designer, you're also now working with an energy modeler to make sure that those standards are met, and you're going to be able to pass the BC step code where it's at that stage. So and the variable in that is the air tightness. And when I first started building, there was really not much mention of air tightness. It was we heard about vapor barriers, and we didn't really hear anything about an air barrier. And in the last sort of 10 years, as builders, we've learned a lot about air barriers and how important they are, and how to create really good ones, and what a good one is. And so the Passive House standard for air barrier, you can see here the Step 5 standard is air exchanges per hour is less than 1. The Passive House standard is 0.6. So it's even lower than the Step Code 5 house, but it's low, and that's the direction that it's going. And to make up for that tightness in the house and to get fresh air into the house, as Ross mentioned, we use mechanical ventilation, and that becomes a really, really important part of the house and part of the system. So this is a photo of my house under construction. It's just around the corner here. You might have seen it. When I came to building my house, I was sort of fresh off a Passive House course, and I was pretty excited about making it super energy efficient. And so I designed it based on some Passive House wall assemblies and roof assemblies that I liked, and got to working with the energy modeler, and he got back to me, and I was pretty sure I was going to go for a Step Code 5 house, and I thought I got the modeling back, and he said, no, it's not Step 5, it's Step 4. He said it's close, but it's not Step 5, and that was I was like, okay, that's not what I wanted, but how can we get to Step 5? And so it became a good learning opportunity for me, because what I realized is that with the complicated shapes and stuff, that really that made it more more complicated, and you had to work harder to get to the lower energy levels. And so he made some suggestions in reducing some of the window sizes, improving some of the insulation values, and tightening up on the air tightness, and those made the difference. So the sort of two aspects again of the system of the house is the thermal side and the mechanical side. And in this, I'm going to just mostly focus on the thermal side of the house, and then next week I was going to talk about the mechanical side of it more. But so here we go. So I'm not too sure how many of you are familiar with building plans. This is we call it cross section. It tells a lot to a builder, and what's kind of unique about the strategy I took here was that all of the black line here represents the insulation layer, and I'm not sure if I can zoom in or what you can see from there, but what's sort of different about this approach is that the structure of the house is all inside the insulation, and what that does is it allows the structure of the house to be in conditioned space. it also allows for a very sort of simple air barrier strategy. And in taking the Passive House courses, the simple way to look at your air barrier is if you can draw a line and connect the dots and connect that line around the whole section of the house, that creates a complete barrier. So it depending on the house, the different connection points are sort of the weak points, and as Ross mentioned, where the air barrier meets the foundation or the windows, those become potential leakage points. And just one other anecdote about keeping in this case, the air barrier on the outside of the framing. Often the other strategy for air barrier might be an interior air barrier and a vapor barrier, but every time we put a hole in the wall, hang a picture, that vapor barrier or air barrier can get punctured in it, and so through the life of the house, it's more vulnerable. So again, this is just another section photo of the house, and it's just pointing to the continuity of that air barrier, or of the thermal the thermal barrier here in this case. But the other thing that we're doing as builders to improve energy efficiency is reduce the thermal bridging. And the thermal bridging is where we have members or members of wood that are transferring heat through to the outside. And so if we can protect or make a separation between the framing members and the outside, that creates a thermal break, so less heat transfer. Again, this slide is just showing a slide of the insulation under the slab, and connecting the air barrier through the concrete to the outside air barrier. So I don't know if I'm is anybody familiar with air barriers here, or is this am I speaking Greek here? Okay. Yeah.
Brad, if you could point to can you show us what you're talking about on the diagram?
Okay. Yeah. Sorry. Thank you.
Your finger works.
Oh, finger. Okay.
Or even
Okay. Got it. Yeah. Okay. I'm doing this. I'm a builder, not a presenter. But so this dotted line here, in this case, is the representing the air barrier, and this would be the air barrier connection between under the slab and the wall here. So again, let's just get on to the next photo. So yeah, so the following are just some photos of the building of the house, and you can just see some of the effort that went into the insulation, and how we really tried to make the house as energy efficient as possible. And really the again, like focusing on the envelope is the sort of mantra that we get in Passive House and in our building technology, because if we focus on the envelope, the other parts, the mechanical parts of the house can always get replaced, and they have a lifespan, so they do get replaced later. But the envelope of the house is what may last 100 years. So we want to make that as robust as possible. So I used ICF forms, which is the insulated concrete or insulated concrete forms. It's like building Lego, basically. They're kind of fun to use. They're light, and they make a great warm, dry basement. So you've probably seen these around. And that's what I used on my place here. I included this slide on the right here. It was a passive house foundation that we did quite some time ago, but it's just as an example of on a simpler form what what you'd expect to do. It's the whole foundation is basically 8 inches of concrete sitting on 8 inches of foam and sort of floating there on foam, and separated from the ground, and that separation creates the thermal break. So that's a passive house approach. Again, the photos here just are showing kind of what we saw in the diagram, that air barrier connection to the ICF foundation there, and then that would continue through, and there would be another connection on the outside of the wall here that is taped to the ICF foundation, and making that air barrier continuous and tight. And then again here, it's just the foam that's goes in underneath the floor, and then the sort of the baseline house that in 2018, this would be typically a 3 inches of foam insulation, and to get to the step 5 or the passive house value, we're looking at more like 12 inches of insulation there. So kind of these sort of surprising amounts of insulation that go into these super energy efficient houses. And the photo here is just showing the assembly on the wall. Again, going back to that diagram that we looked at, where the framing was not connecting through, and we've got a thermal break here between the inside and the outside of the house, so less heat transfer, and with the foam that went on the outside of the house, we've got 2 layers of 4-inch foam that when we apply it, we lap it so that there's it's creating not leaving gaps in the foam, and so these are just to show you again, like the extent that we have to go to now to get to the energy efficiency levels that are going to be expected of us in basically 7 years from now, and this will be throughout the industry. So on the right hand side here, we've included this as it's a really important part of the thermal envelope system. It's a passive house rated wall window rather, and you can see it's triple pane, and it's got pretty large gaps in between the panes, and the frame is pretty advanced with multiple seals on the opener, and lots of insulation. So these windows, the passive house windows, are going to be probably 4 or 5 times more efficient than sort of standard windows that we'd buy. To the point of the envelope as a system, it might not make sense to put such a robust window in a house that's getting a retrofit that might not have the rest of its envelope being kind of as robust as this. But when we're trying to build to the sort of passive house level or step 5 level, these are the kind of things that we use. So again, if you're building an energy efficient house, one of the important things to remember is to get your friends to help you, because it takes a lot of labor. and so no, but this is again a picture of the roof and meeting the wall, and basically just kind of showing the continuity of the insulation running up the outside over the roof and outside of the wall, and again the fact that it's on the outside of the building, it sort of eliminates that thermal bridging that's typical with the more traditional construction methods. And again, here we've got, I guess, 12, 15 inches of foam on the roof, and the parapet sitting on top of that, and that again is creating our thermal break, so that the heat's not transferring, through the framing and out. So all these are details that that we consider with super energy efficient housing. This detail is showing a floor cantilever, and floor cantilevers are kind of traditionally heat loss areas that we have to give special attention to. If the walls are lining up, it's not problematic, but when you have an exposed floor like this, you have to make special effort to make sure that's super insulated. And so the approach here was to spray foam in between the joists, and then bat those joists, fill the gap with bat, and then carry on the air barrier on top of that. So basically that blue wrap that you saw in the previous is our air barrier, and that would be continued and taped over here where it's to make it continuous. And this spray foam also helps act as an air barrier. So sort of doing double duty there. But and then to eliminate the thermal bridge of the framing that we see here, we cap that over with 4 inches of EPS foam, and it makes a pretty robust detail there on the overhang. Oops. Okay. Oh, settle down. Okay. Oh, can we go back one? There it is. Okay. Yeah. So the last photo before we get to the little video that I've got is just showing the penetrations in the thermal envelope here, and again, just the level of detail that you have to consider when building these super energy efficient houses. Here we've got the refrigerant lines coming into the heat pump head, and so making a clean kind of avenue for them to go, and then we were able to tape the conduit to the air barrier, and we'd spray foam that to close it up, and probably caulk it as well, because this is probably going to leak a little bit of air, and we don't want that. We want to minimize that as much as possible. And again, here we've got a penetration for a conduit that's going to be to accept the solar, the future solar that we're hoping to put in, and again, just detailing that to make sure it's sealed at the air barrier and insulated, and yeah, that's again sort of the level of detail that we need to consider when building, and of course this comes at sort of a cost. So we're trying to as we get towards step 5. Improve our methods and get more efficient and make it more sort of the norm, I guess, so that we can do it more efficiently and be not let the cost of it get too out of hand. And so the sort of like a report card day on any builder is the board or test, and you see how airtight you've made the house. And so we did put a little video together of the mid-construction blower door test, which isn't mandatory in the step code, but it's really recommended, especially if you're trying to get your air tightness to levels of under 1, or passive house, or just if you're trying to get to those super tight levels, because it gives you an opportunity to make fixes if need be. So anyway, here's a little video that we made of our blower door test, and it gives you an idea of what that looks like. And if I can just press play.
Congratulations. Sounds like a lot of tree on the coast. Great job. All right.
Right on. Okay, well, thanks, Nigel.
Yeah, thank you.
Okay.
All right.
Thanks, Karen. Yeah, so that was our blower door test, and we were very happy with that result. I think that's where I'm going to sort of pause it. The last part of my presentation gets into the mechanical side, and I'm going to leave that until next week. But just going to pause it there and hand it over to our next presenter. But if there's any questions, please go ahead now. Yes.
A couple of questions.
Okay.
What's the cost roughly per square foot to build a home like that?
Yeah, that's a good question. And thanks for putting me on the spot here. But no, it's a fair question, and you know, our building costs obviously these days have you know, ramped up, especially in the last 4 years, and you know, the appetite for you know, going the extra mile on this is you know, getting a little bit less, but as the step code is sort of pushing us towards that anyways, it's you know, it's that push and pull. So to answer your question, I think it's easier to say it's more than what the conventional house would be, but don't forget, now we have to build to step code 3 anyway, so it's not a huge stretch at this point to get those a little bit further. But yeah, there is a premium to it. You know, what exactly that is, it kind of probably is going to depend on the form of the house. My house was a little bit, you know, it wasn't just a box; it was a bunch of boxes, kind of thing. So it was a little bit more complicated. But yeah, I mean, I'm going to say, you know, throwing out a number, maybe, you know, 15 to 20%, probably more than the typical house.
Fair enough.
Yeah.
Second question, with all that cement and foam, how sustainable to earthquakes is it?
Yeah, fair question too. So most of the most of the structure is wood frame. So the actual structural elements are wood, and so that's how it's been engineered is you know, for the wood frame. So that's you know, that's a pretty good you know, earthquake structure. Yeah. Go ahead.
Thinking of wildflowers, how is the all that insulation extra flammable?
Yeah, no, it's another good question, and the insulation, I guess there's some flame retardant in it, but the sort of a preferable choice to that might be Roxul. No, the Roxul, I chose not to use Roxul. I liked it as a product. It's really environmentally sound, but it was about 4 times the expense of the foam. So I thought I had a limit to it for me. So but that's a good question. The foam could be a problem.
Step 3 is the provincial, right?
Step 3 is what we are at locally, and I believe it's and I believe it is provincially as well. But I could be wrong on that. There might be areas of the province that are elsewhere in the step code.
Most of the lower mainland municipalities have actually moved beyond step 3.
Okay. Yeah.
Most of like Burnaby, Vancouver has their own code, which is comparable, and they're way above. But Richmond, Burnaby, Surrey's still at 3, but a lot of them, municipalities can choose to go farther faster. There's the provincial scale you have to stick with, and then and there's also another code you'll hear, just since we're not rushed for time. There's
Yeah. Go ahead here.
Sorry. There's another code you'll hear, the zero carbon step code, and that's starting to be introduced as well. And right now here on the coast, we're at measure only, meaning you don't have to achieve it. But that's going to be a measurement of the carbon use within the home, so gas use and propane and those sorts of things. So there's 2 different codes. And again, municipalities can choose to go farther, faster. So like Richmond, for example, has step 4 if you're such and such on the carbon, or step 5 if you're on the, so they can have different combinations. So it's a bit, but here on the coast, it's pretty straightforward. We're at the provincial minimum, and my sense is from the SCRD told me they were planning on staying there to try to encourage building here. And on the zero carbon, we're at measure only as well. So, but just remember, if you see the word step code, if you see zero carbon, that's actually a different scale of measure.
Sure. I would imagine
Thanks, Ross.
colder climates like Whistler, Pemberton, it should be step code 4 or 5 at least. No?
It's really up to the municipality to decide, but they have to adhere to the provincial
Are they
minimums.
shooting towards that?
So Miguel, depending on what climate zone, you're going to have a different.
Oh.
Sorry, the question was, or more of a statement to say that areas like Whistler and those colder areas must be advanced in the step code. And what I was going to say is that they are different climatic zones, so they would be held to higher standards just because of that. So it's more about it has to be suitable to the climate zone that they're in. Yeah.
Brad, whenever I'm pouring concrete, I'm always packing like crazy down the foundation that it's on, and you're laying concrete on foam. Doesn't that weaken, like, would you be worried that the concrete was going to lose its foundation because it's on something soft?
Yeah, that was my first reaction to seeing that kind of construction was like, is this really going to work? But yeah, it does work. It's engineered for that type of resistance, and the foam that the foundations are sitting on are generally geofoam, so it's got a higher compression strength to it. It's used in bridges and for infill, so it's the actual pound per square foot. I guess it's suitable for that.
So your concrete floors aren't squeaky?
No, we go. No, they're not.
It's not very powerful, Mike.
I know this is gonna be a guess from you, but building an airtight home or an energy efficient home, you have to be saving on operating costs. You know how much you spent, if you call it extra to get that energy efficiency. Do you have any sense of the payback period?
Yeah, I mean that can be fairly easily calculated. We at the end of the project, we get an EnerGuide rating, so that gives you the estimated consumption throughout the year. So you'll see sort of how much you're using, and then I guess you can compare that to what you spent. But yeah, it's pretty quantifiable. Thanks, you guys.
Thank you, Brad.
Okay, off we go. So just in case people didn't get our names. Okay, so what you're going to learn today, already partly there, but the home energy basics, where to start, developing the plan, so that was Russ. And sequencing of actions is part of what we're going to talk about, and cost and benefit calculations for part of it. We're going to do cost and benefit quite a bit more next week as well. Next week, we're going to talk about executing your plan, how to get it done, how to pay for it, and everything you wanted to know about grants and loans and the sort of financial incentives from all over the place. So that's where we're going. And we talked about really expensive stuff. I want to remind people that there are things you can do tonight, or at least tomorrow if you buy your light bulbs. People kind of don't really think about it enough. If you haven't all switched over to LEDs, I want you to take this, all I'm going to say about lighting, but it's an important fact. If you still have your old 60 and 100 watt light bulbs, It is costing you a lot of money. It is not worth trying to wait until they burn out to replace them. Okay? If you look at the cost, I just picked, a couple of years here. That's what it takes. 2 or 3 years running 7 hours a day. The bulb is pretty cheap, but it hardly lasts any time. So the bulb cost is $8 per time period. They're all set for time period. The LED lasts way, way longer. Now, depending on which one you buy, this one was a really good long-lived one from Amazon. But if you go to Canadian Tire, they've got some that are half the price, but they only last for 1,500 hours. You can look at the box, it tells you what it's rated for. But you can see it's 40 cents compared to the $8 for the same amount of time. So for that 30,000 hours, you'll spend $8 on the incandescents. Energy costs, though, dwarfs it. You're only using 13 watts for the LED, and it gives you the same amount of light as this is for 100 watt. So you're using $70 worth of electricity compared to $9. So factor of 8 or 9. Go out and replace your light bulbs. Okay. Home heating and cooling is the next one. If you've got an oil furnace, don't walk to replace your unit. If you're using propane, I know a lot of people are using propane, again, major reason to change. This shows 100 gigajoules is a typical amount for a home. That's basically what BC Hydro says for the average home on the Lower Mainland. If you've got a house like mine, which is 1974, that had an air exchange ratio, Ross tested it was around 4, not 0.56. So when the wind blows, you can see things flutter in my house. So that's one of the things I'm working on, is improving my envelope. But anyway, 100 is the average. An oil furnace costs you $8,000. Natural gas is the cheapest, but a heat pump is right in there. So that's why if you care about the planet and you've gotten yourself to the point where my old gas furnace is 20, 25 years old, it's time to replace it. Please don't replace it in kind with something that's going to last another 25 years. You can replace it with a heat pump for approximately the same amount of money, and it has almost no greenhouse gas emissions. So please do that. Central air is about the same, and geothermal, it costs a lot more to install because you have to have lines outside and so on, but it's still worth it. So if you look at the replacement cost, if you have an oil furnace and it's died, it'll cost you about $15,000 to put in a new oil furnace, or a propane or natural gas, or mini splits. They're maybe $20,000 if you have, because you're changing the system, so it's a little bit more expensive. However, if you look at the far side, what's your payback? So, going from an oil furnace, you get the very worst case is a 3-year payback with the geothermal system by switching to the new one. And you can see switching to a heat pump, less than a year. Okay, so that's switching from an oil furnace. But most of us don't have the oil furnace. So I've just redone it here and said, okay, if you've got baseboards, actually this is all compared to natural gas. So if you've got natural gas and you switch over to baseboards, it will cost you an extra $2,000 a year. So that's why nobody's going to baseboards. They're cheap, but they're incredibly expensive to run. They have 100% efficiency. In other words, 1 kilowatt of energy going into the unit gives you 1 kilowatt of heat. Whereas a heat pump, it's pumping heat. So 1 kilowatt of energy going to the motor for the compressor will give you 2 or 3 kilowatts of heat in your house. So that's why it's there. We're saying like 250% efficient. I hadn't put the efficiencies on, it was on the previous page, but the heat pumps are around 250% efficient. That's over the whole year. And the geothermal are 3 and 4, depending on what kind of system you get. So they're very, very efficient, use very much less electricity, but then the payback, going to the mini split, 2 years, 4 years, so on, and probably even less because there are incentives. So if you qualify for incentives and then you do it with their interest-free loan, and you put that $25,000 in some sort of investments, don't do Bitcoin though, because it's going to but if you put it into even a GIC at 3-4%, then that payback is even better. So that's what I wanted to show. We will go into how to calculate this stuff later, but that's coming next week. But overall, please, heat pumps seem to be the answer at the moment. There's probably other technology coming, but right now, no question, it's the way to go. Okay, and as a Tesla owner, I have to say, I have a hard time with that. I bought it before I knew Elon was going to go into politics. But anyway, it's a great car. And there are other great cars as well. The important thing with them is, again, dramatically reduce your greenhouse gas emissions. Range is not an issue anymore. They all go 300-400 kilometers. If you get the Teslas, they're up to 5 or even more than 500, way more than my bladder can take. So, you just stop when it's time for your bladder, plug in, go get yourself a cup of tea or something, come back 15 minutes later and it's ready to go another 100 kilometers. Way lower maintenance cost. It's got, I think they were saying about 50 moving parts as opposed to 2,000 for ICE vehicles. So, no more oil changes, all that stuff. 95% lower greenhouse gases here because we have hydro. An example, Ford F-150, it will save you $22,000 over the course of 4 years, just comparing gas to the electrical bill if you plug it in at your home. So, okay, that's all I'm going to talk about EVs, but again, please make your next car, at the very least hybrid, but even better EV. Hybrid is just a really efficient gas engine. You still have all of the maintenance and so on because it's still a gas and internal combustion engine. Okay, building envelope. So we've had a major lesson. I wasn't sure if I was going to go first or last at this thing, but I'm going to refresh your memory. Insulation, vapor barrier, and I've learned a new thing, air barrier. So my house, my air barrier is the interior vapor barrier, and of course, in 1974 house, that's a strip of tar paper hooked up to my 1 inch of insulation that was stapled to each 2x4. So it's kind of leaky. And everybody else who has a 1974 or older house, it's probably just that bad. So there are many things you can do to retrofit, and if you have questions, this man knows all about retrofitting too, although he much prefers to build new, I'm sure. Okay. Improve the weather stripping, seal the air leaks. That makes a big difference, especially in an older house. upgrade your windows and doors. If you've got single glazed, I'll be going through a few things next week about showing you what the difference is between a single glazed, a double glazed, a super duper double glazed with argon fill and so on, or passive house, and show how much that can save you in energy and dollars actually. If you have south-facing windows and you find it hot in the summer, you can put an awning. It makes an enormous difference. And I highly recommend you ask for a solar awning, because a solar panel makes a very, very effective awning, about the same price, and you get a payback. So, and if you have an older house like I do, put in an HRV, because it dramatically improves the comfort of the house. It still blows in my house when it's windy, but now my air is fresh and I don't have a constant inflow of air because it's neutral. My house isn't under negative pressure anymore. So my wife has let me lower the temperature to 72 now. I would like 68. However, 72 is a big improvement over what was there before, because it was drafty, and so. Okay, now, I care about renewable energy as part of the Solar Energy Association. That's been my thing. I'm a chemical engineer. I've been super interested in solar energy since I graduated back in '78, and it's only gotten better. There's a great slide coming up for somebody showing how much solar energy cost has dropped, and it's definitely worth doing. Absolutely worth doing. If you have a house that isn't too shaded, you will save money on it. So people talk about geothermal. This is true geothermal. Is, you know, the hot springs and so on. They put pipes down and they use that heat to generate steam to drive a turbine or to heat a building or so on. That's true geothermal. When people talk about I have geothermal in my house, typically what they really mean is the heat pump that is using the heat of the ground rather than the heat of the air to heat your house. Got the name blanked out here. No, I don't see it. Okay. Wind. This is the unit that's sitting up on top of Cypress Mountain.
Gross.
Yeah, Gross Mountain. Yes, thank you. If you go look at it, it's hardly ever turning, and it is in the very best location. It's the very top of the mountain, right? No trees around it and so on. We simply don't have enough wind here on a consistent basis. We get gusty days, but there's not enough wind generally. So if you're thinking of how do I make power, if you're in the middle of the Rockies, probably great. You know, Calgary has fantastic wind. We don't. So it's not really something to worry about here. Which just leaves hydro. We have wonderful hydro reserves, but very few people have got a mountain stream going through their property. And even if they do, you have a really, really tough time getting a permit to harvest that energy. So again, for us, it's not an issue. So what does that leave? Yes, solar. Solar is super easy. You can heat your domestic hot water. That saves a lot of money. This unit can generate 80-degree C water, so you actually have to put a tempering valve after it to make sure you don't injure people. You can heat up swimming pools or spas or things like that with a simple mat. You can buy a mat like that for maybe $300 and use the pool pump. When it's hot out, there's a little sensor there, turns your three-way valve automatically and pumps the water up through that and back to your pool. When it's cool outside, it just switches the other way and just simply goes back and recirculates through the pool. I have one of those on my pool. I'm lucky to have a pool, I must say. And from May until September, I keep that pool at 82 degrees Fahrenheit, which is 28, I think. But anyway, my meter is Fahrenheit. I've got an old meter. 82 degrees Fahrenheit. Super lovely. No energy whatsoever other than the pump going around like it would have anyway. So that's totally worth it. And then solar panels have gotten better and better. Those are the ones on my house. They're from 2014 when I first bought them. I waited until BC Hydro had their net metering system because that was the very first time that you could get panels and not lose money. I'm a geek. I'll admit it, I'm a geek. So as soon as I could get it without actually losing money, I did. It was break even back in 2014. Completely different 11 years later. The prices have come down about, I'd say 60% or more. He's got the real numbers. So I have since added to my system, and I've now got myself up to net zero, which includes a secondary building on my property that I rent out. So all handled by solar. Okay, now we're going to school, because a lot of what's coming up, you need to know the terminology. And you've probably all heard about volts. It's a 12 volt battery on your car, and that's 120 volt in the plug here, and maybe your dryer runs on 240 volts. So that's basically, you think about it like the water pressure in a dam. So you have a certain amount of potential. It doesn't have to go anywhere, but that's how much voltage is sitting in that battery ready to go. Amps are a measurement of how much electricity is actually flowing. It's actually the current. It's measuring the electron flow. So that's how much you're using. And then watts are just the sum of those two. Watts are equal to amps times volts. Because 1 amp at 12 volts is not anywhere near as much powerful as 1 amp at 120 volts. That one will fry you. The 12 amp one, you might feel a little tingle, but that's it. Okay. Kilowatts. So that's just 1,000 watts. And it's the rate of energy use. So in cars, we think of horsepower. It's a 200 horsepower, or if it's a Tesla, it's 400 horsepower, whatever it is. That's what it's capable of. If you put it, you go. But it really matters is how long have you been using that power? So you might have a 200 horsepower car, but if it's sitting in the garage not going anywhere, you're not using any energy. You have the potential to use the energy, but you're not. However, if you have it and you use it for an hour, now you have a kilowatt hour. So that's the thing that BC Hydro charges you for, right? Your 14 cents per kilowatt hour on your bill. That's the consumption of 1 kilowatt times 14 cents per kilowatt hour. So an LED light bulb might be 10 watts, which is 0.01 kilowatts. But if you run it for 6 hours, now it's 0.06 kilowatt hours. Your electric range, or your oven, typically is about 2,000 watts. So that's 2 kilowatts. So if you have it on, baking big potatoes or something in a roast or whatever you do for a couple of hours, you have just used 4 kilowatt hours times 14 cents equals, there's your bill. You do it all over 2 months, eventually your bill adds up. Okay. In solar, you'll hear people talk about watts per square meter, and that's basically how much solar energy will land in this particular square meter. ideally on your roof. So you want to measure that, and from that you can estimate how much your solar panels will do. You don't have to worry about that, but you may see that in a report that a person does on your solar panels. And then the other thing is direct current and alternating. So again, probably you already know this, but direct current is like your car battery, where you've got a positive and a negative, and the current always goes in that direction. Alternating current is like this stuff, and every 60 seconds it changes directions. So it's going this way and then it's going that way, back and forth, back and forth, back and forth. Still power, but different form. Okay, I'm stopping here because we're going on to more stuff. So are there any questions from any of us at this point?
Hi, can you hear me?
Yes.
So thank you, that was a great presentation. And thank you, Brad, as well, and everybody, it's all been great. I'm just wondering, when you say that your house is net zero on solar panels, I've looked into different options as well, and I was told that solar here wasn't a great option because of cloud cover in the winter months. So you're still on the grid, I take it?
I'm on the grid. I'm taking advantage of the BC Hydro net metering. So you're correct. In the wintertime, my solar panels make 1/10 of the power, of the energy, they gather that much energy, that they do in July.
But does BC Hydro average that out over the year, just like they might a hydro?
That's
bill?
right. In the summer, I have more than I consume,
Yeah.
and it goes backwards through my meter. With a smart meter, it reads to and from.
Yeah.
So that's good. Most of us have smart meters now. So they measure how much they sent in at night and how much I sent out when the sun was out. And at the end of the 2-month period, they say, you did this much and that much. And in July, I make way more than I use, and that I get a credit for that. So I've got a little thing that says you have a 2,000 kilowatt hour credit. And then the next month, it does it again and again and again. By the time I get to about September, I have a lot of credits. And now winter comes, they start having water behind their dam. I start losing the sun. They are my battery. So I start using more than I make, and they start taking those credits off. So on my anniversary date in March, I end up with very close to zero. So basically I don't pay anything any of those months except for the $11.30 or whatever it is for the connection fee every 2 months. And that basically is my electric bill. So by putting in solar, it's like buying a bond. I have bought my power for the next 25 years at today's price, no inflation.
Okay, thank you.
Do you have the sun pretty much all day where you are?
Yes, I have. I'm lucky. I have a very, very. I don't know if you noticed the picture that I've got it on the house. I have almost a flat roof, so I was able to angle it really well. I have it slightly angled to the west of south, which in our area is good because in the morning you usually have, at least where I live, I'm only like 400 yards from the ocean. Meters. Sorry. I haven't completely gone to metric. When we're in the morning, there's often fog or low cloud that burns off by noon. So by having it slightly west, I get lots and lots of sun because all afternoon it's completely clear, and there aren't any trees in front. Yes.
When you bought your Tesla,
I'll pass this to you.
when you bought your Tesla, did you put an electric box on your house, right?
I did. When I bought my Tesla, I put in one of those 110 volt plugs right next to the Tesla. I plug in. This only gives you about 8 kilometers per hour. But on the coast here, I usually drive 30 or 40K at most during the day. So it easily recharges overnight. There are some incentives right now that make it so you can buy the faster charger, and I think I will take advantage of it because you get it almost for free. That will charge it up in maybe 3 hours instead of 8 or 12. Yes.
Jerry, those figures that you were listing for the payback for replacing your heating system,
Yes.
what if there's nothing wrong with your heating system? If would the payback be worth it at all? If you had baseboard electric or a perfectly good natural gas heater, would it ever be worth it to switch to a heat pump?
I care about the environment, so yes. You get rid of the greenhouse gases. And you get rid of chance of carbon dioxide, carbon monoxide, methane, assorted gases in the house, right? As soon as you get rid of that, you can't have any carbon monoxide anymore. That's one of the possibilities of having a combustion source in your home. So I think it's worth it. Certainly, if it's getting to close to end of life, please do it. If it was just put in 2 years ago and it was a mistake, I understand, but
Thank you.
I'm showing my bias. Yes.
Do you have any thoughts on skylights? Because
There's people watching who want to hear what the question is.
Can you hear me now?
Yes, good.
No. Do you have any thoughts on skylights? Because we have 5 in our house, and I curse them sometimes because they get so hot in summer and they leak heat. They're not leaking through a crack,
Yeah.
but just through conduction in the winter.
Good point. I have 3 skylights in my house. 2 of them are 4 foot by 4 foot. They're very big skylights. They were the old plastic dome style. Very classic 1974 skylights, double glazed, but they didn't really insulate very well. I replaced them with triple glazed argon filled when I had my roof redone, and the difference is astounding. Absolutely, unbelievably astounding. If you make that change, you will very much notice it, because all the heat is up there, so there's a big temperature difference between the outside and the inside. And I have access to them, so in the summertime when it gets hot, I have like a Roman blind that I put across, so it lets a bit of light through, but basically shades the house. So, and that was when they installed them, I had them put a couple of grommets on each end so that I could just put it over and attach it.
That goes on the outside.
On the outside, yeah. Yeah, and also on the inside, you can do stuff, but the heat is already in then. So it reduces it, but it doesn't do anywhere near as much a good job as putting it outside. On my south-facing windows, I did the same thing. Instead of putting drapes on the inside, or whatever method, I put Venetian blinds, aluminum Venetian blinds on the outside. They can go up and down, they can tilt and so on. They're very robust. If you were in a hurricane, you'd close them and protect your windows. And they make a gigantic difference, because now with the tilt I can still see out, I get everything, but there's no sun actually getting through. So I've eliminated all that thermal gain. I've eliminated all my furniture getting bleached white and so on. So that was a really good purchase as well. Little things you can do that make a huge difference. I have to stop now. Because
Should we move on to Liam?
We need to get to Liam. Yeah.
All right.
Thank you.
Good evening. evening, everyone. Thanks for coming out tonight. My name is Liam Bonser. I'm the owner and master electrician at New Bond Canada, a company that I started in the summer of last year after many years working as an electrician at Olson Electric. One of my specialties, in addition to doing all other electrical work, is doing solar power installations. And I've been privileged to be part of over 100 installs, mostly on the Sunshine Coast and a few in the Lower Mainland. So that actually makes me one of the most experienced solar installers in all of British Columbia, something that I'm very proud of, and I really, really enjoy doing it. So currently, solar is about 50% of my business. The other 50% is other electrical, and that's definitely something that I want to keep going as I grow the business. When I'm not working, I have a wonderful wife and a 2-year-old son who I enjoy spending time with, and I also have another one that's due in about 2.5 weeks. So, so that keeps me pretty busy. I grew up on the coast, and then after high school, university left for a few years. I was in Edmonton area for a bit, and then Kamloops for a bit. And when you grow up in a small town, you kind of have this, oh, I'd like to get out and see the world and experience different things. And then after a while you realize, where I lived before it was a pretty great place. So came back 7 years ago and have been really happy to be back and really enjoying working here and now running my business here and being part of the community. So I'm going to take you way back to the very first solar panel when this all started. So this was New York in the year 1883. I don't know how many of you have been to New York. I actually had the privilege of going there last summer. So for those of you that know New York at all, this was on a building that was addressed was 33rd 82nd Avenue, which now looks all different, but it's very close to the New York Public Library. It's basically kitty corner to it. So even though it doesn't look like this at all, I actually walked in front of the building that originally would have been on back in 1883. So the inventor of it was Charles Fritz. We don't have a ton of detail about it. There seems to only be one picture of it. But what we do know is that the efficiency on it was about 1%, which is extremely low. But what it did is it proved that solar power actually worked and you could capture energy from the sun to make electricity. So it took it from a scientific problem of, is this even something we can do, to say, yes, we can do this. It's now sort of an engineering problem. There's a lot of steps to make this more efficient. The other problem with it is that it used gold on it. So we don't know what the price on it was, but it would have been very expensive. So not very practical, but it showed the world that yes, this is something that we can do. So after that, there wasn't really a practical application for solar panels on Earth in terms of making the price point make sense. But what really accelerated everything is when we started going to space. Initially, the first crafts that went up would just go up for a short time and then come back down. So you didn't need a way of generating electricity when you were up there. You just had a few batteries on board. But pretty soon, for exploring and satellites and things like that, what we realized is we need a way to be able to generate electricity in space. The best way to do that was through solar panels. So the very first solar-powered satellite in space was Vanguard 1, which was launched in 1958. The next application where solar panels made sense was at very remote locations that had electricity demand where you either had to bring in fuel, which was expensive and unreliable, and also in very remote locations that made it hard to get to. So the perfect place to do that was on lighthouses. So this is actually from the very first lighthouse in the world that had solar panels. It's in Japan, and it was put on in 1966. The company Sharp was in Japan in the early 60s, was working on the technology to make it viable for use on Earth. And before they had electric for lighthouses, you would have to use a gas for the light, which was expensive, high maintenance, and you had to bring the gas in all the time. So this was the perfect application for solar panels. So the other interesting thing is, and that's great about solar, is it's solid state. There's no maintenance. So a lot of these lighthouses that were getting panels in the 60s and 70s, a lot of them actually still have their original equipment because the solar panel doesn't wear out. It just very slowly degrades over time. So we like to think that solar panels, we say they'll last for 25 years, but there's no reason they shouldn't last a lot longer, and historically it's shown that they actually do. So this is a graph that shows the crazy cost reduction in solar panels from 1975 to 2021. So back in 1975, which was when commercially solar was just starting to take off in California and some other places with really large government subsidies, but the cost, and this is just for the panel itself, no other gear, was basically $100 for just the per watt for the solar panels. Now, fast forward to today, this graph ends in about 2022, but the price has dropped over 95%. Now we're around 25 cents as opposed to $100. So the reduction has been absolutely staggering. And the nice thing too is with how the global supply of solar panels is looking, that slowed down a little bit, but even now, every year they're getting very slightly cheaper. So how does a solar panel actually work? Now, I'm not sure how well you can see this graph, but what happens is that there's photons that are coming from the sun. What happens to those photons is about 20% of them we're able to capture in a solar panel. The two biggest reasons we can't capture more are the fact that some of them have either too little energy to be captured by the panel, or some of them actually will have too much, is one reason. The second, even bigger reason is the fact that silicone, which is used in solar panels, is only able to capture part of the light spectrum that's coming from the sun. It's more on the blue-green side of the light spectrum as opposed to sort of the red-yellow side. So the next breakthrough in solar panels, which isn't available commercially yet, but is something they're working on in the lab, is having solar panels and using materials that are able to capture a bigger range of the light spectrum, increasing efficiency, but it's probably going to be quite a while before we see that. So after this, we capture the solar, the electrons from the sun, the solar panels then produce direct current, which is how they're set up. But we don't want direct current unless it's just a little panel that you have on your RV or to charge the battery on your car, keep it charged. The rest of the grid in our houses use alternating current. So we have to have some way of changing that direct current to alternating current, and the way you do that is with an inverter. And when you do a solar system, there's two ways that you can do your inverter. One is called a string inverter, where you basically hook all of your solar panels up together, and then you have one big inverter that's converting all of them to direct current to alternating current. Or you can also use a microinverter, and in that case, usually either each panel or a group of two panels will have its own little inverter on the roof underneath the solar panels. So in terms of breaking down how the systems are constructed and the ones that we design, we like to think of them as off-grid or on-grid. So on an off-grid system, that would be if you have, like, even could be a travel trailer or a cabin or someplace that's not connected to BC Hydro. In that case, what you do is you will have a system that is closed and will use batteries to back up whatever loads you need when the sun isn't running. So in that system, how it works is the solar panel first goes to a charge controller. And why that's needed is if you don't have the charge controller, you'll overcharge your batteries if there's more sun than the batteries can take and whatever loads you have on are using. So in that case, what it'll do is it'll start to ramp down how much solar is producing and will automatically change how much solar is being fed into the system. Then from there, you go into an inverter, and that inverter is changing the direct current to alternating current. So before the inverter, you go into the batteries, which are controlled by the charge controller, and then some of the, depending on if it's sunny or what the usage is, Some of it will go into the batteries to be stored, and some of it will be used by the inverter right away to power whatever loads you are using. The other system that's for solar that's much more common and what most people have for houses here, because most of us are on the BC Hydro grid, is a grid-tied system. So in this case, it's similar, except instead of having the charge controller and the batteries, you're basically using BC Hydro as your battery. So, and Jerry alluded to this earlier, what you do is when it's sunnier and you're producing more than you use, you send it back to BC Hydro through your smart meter. You build up an energy credit, and then in the winter, when you're using more than you're producing, you eat back through that energy credit. So there's a few factors that affect how much solar energy you can produce from based on your location. The biggest one is how much shade that you have. So if you have a lot of trees surrounding your house, it could easily be possible that putting solar on your house doesn't make sense, because you would never be able to pay back the cost of the solar system due to the shading that would be limiting your production. Another factor is the angle of tilt of the solar panels. So one thing that people think a lot is, oh, my roof is only, let's say, 20 degrees, but actually I want 45 degrees because I want to maximize how much power I generate year round. But here in BC, it's actually not the case unless you're off grid, because what we're actually trying to do is produce the most amount of solar energy on the longest day of the year. So generally, the roof pitches that people have here are actually fairly close to not perfect, or close enough that it doesn't really make a difference. The other thing is, generally you want to be south-facing, but if you don't have a south-facing roof, you can go east or west-facing, and that is about 12% less efficient on an annual basis than facing due south. The other interesting thing is, it doesn't apply here yet because we don't have enough solar power, but in areas of California, where they've had solar for a lot longer, what's happened is, in some of those places, there's so many people that have solar panels facing south that during the day, especially in the summer, the grid can't take any more power. So in those locations, if you want to add solar to your house, they'll say, you can, but only if you can put it east or west facing and produce when not everybody else in your neighborhood is producing. And in terms of how much, so a lot of times, even when it's cloudy, you're still producing some solar power. So on sort of not a short, dark winter day, but let's say a cloudy spring, summer, fall day, you're producing about a third of what you'd produce on a peak sunny day. So how much power do you need? So in British Columbia, the average house that heats with electricity, so that would be electric baseboard, uses 15,000 kilowatt hours of electricity per year. You can check how much you're using either by looking at your hydro bill, and it'll show you in graph form throughout the year, or if you log into your account, you can actually go in and say, tell me from this date to this date how much power I used, and it'll generate you a monthly or bi-monthly report and add it up and say this is the total amount of kilowatt hours that you used. The thing with how our electricity rates in BC work is there's two options that you can have for your electrical rates. One is time of day billing, where you're charged more during certain times of the day than others. Or you can also just have it where it charges you a fixed amount throughout the day. But regardless of which option you choose, we have here what's known as stepped electrical rates. So you get so much per month at a lower price for electricity, and then which is around 10 cents per kilowatt hour. Once you've gone through that amount, they'll bump you up into the expensive electrical price, which is around 14 cents per kilowatt hour. So even if you can't get your house to net zero, which meaning you generate the same amount of electricity that you use on an annualized basis, the big saving is keeping yourself out of that step 2 rate. So even if you can only generate 70-80% of the amount of electricity that you use, it's still worth it to go solar just for keeping yourself out of those more expensive rates. Also, a lot of times, those will be houses where people, let's say, have old baseboard heaters or that are drawing a lot of electricity, or they haven't done any building envelope upgrades, their house is quite leaky, so the amount of energy they're using is more than it could be otherwise. So let's say you can generate, if you improve your building envelope, add a heat pump, you take your electrical bill down by 30%. Well, now instead of, even though you're generating 70%, now you're up to net zero as opposed to 30% under. All right, any questions?
Do you have to clean solar panels?
That's a great question. So the question was, do you have to clean solar panels? One of the nice things about solar panels is they have a glass finish that's very slippery, so things don't adhere to it very well. So generally, if you get a good rain, it's enough to clean off the solar panels. Now, depending on what you have for access, sometimes you notice, oh, I got a bunch of needles up there, or some leaves, or a branch of some kind. It's good to take that off. But generally, you don't have to worry about cleaning them. The other thing is, on a solar panel, there's a little bit of a gap where there's no silicone between the metal frame on the edge and the wafers. So there's a thin layer of algae that likes to grow right around where those two join, but they're specifically designed that doesn't affect the production because that's not in an area that has a silicone solar cell.
Is there a particular style of solar panel that works better on roofs from your experience?
So the question was, is there a particular style of solar panel that works better on roofs? That's a very good question. The biggest difference with solar panels is more from a visual perspective. So a lot of people have said, oh, I'd like to get solar, but the fact that it has a silver frame and it's got those blue wafers that I look at, a lot of people didn't like that because they thought it was ugly. Now some people didn't care. So what the solar industry moved towards is doing an all black system, where you have a black frame and the cell and all the silicone is black, everything's black, and we use black clamps on that, so that really improves the aesthetic overall. In the past, you had to pay a massive premium for that, so a lot of people didn't opt in, but now, because the prices have dropped down so much, even in the 7.5 years that I've been doing this, black frame, all black modules with black racking is standard. Now, occasionally there'll be some people, if they really don't care if there's certain promotions or whatever, they can use the silver and blue panels, but generally people it's more about the visual aesthetic. In that case, we use all black panels.
What about the timing of changing your roof?
Okay,
How does that work with solar
great question. So question was, what about if you have to change your roof? So if your roof only has, let's say you have a Droid roof, which is the asphalt shingles. If it has 5 to 10 years left on it, what we would say in that case is replace your roof before putting the solar on, because that just makes the most sense from a cost perspective. If you have, if let's say it's about halfway used and you have like 15 years left, and you'd say, well, the panels are going to last for 25, but I only have 15 years left. In that case, assuming the roof was in good shape, we'd say it probably would be worth it to put solar on, because in the future, when you have to re-roof, a lot of the work and cost of the system is the solar panels and inverters themselves, and also the time and material it takes to run the wiring from your roof down to feed into your electrical panel to feed your house and back to the grid. Especially on older houses that aren't solar ready or have some easy way to run wiring up, one of the big time commitments to the job and also challenge of the job can be getting the wiring from, let's say, the first floor where your panel is up to your roof. So if you do have to replace your roof, all of that work is already done. So what we can do, and we've done this not because a roof was nearing the end of its life, but when the roof was initially put on the house, thankfully it wasn't anything to do with us, but where the original roof, where there were seams that lined up, they made the shingles too short. So short, only a few years in, it started to leak. So they had to fix all of that. So we were able to roll in. We basically take the solar panels off, take the racking off, sort of unclip everything and roll it out of the way. That takes us about a day. The roofers come in and do everything they need. We just come back, put everything back, and basically roll the system back out with the racking, the panels, and the wiring, which is about another day to put back. So in terms of added cost to your system, even if you do have to re-roof before the end of life, which we say is 25 years for the solar system, the extra cost isn't that much. The other thing too is that even if it's that's also a good opportunity at that point where you could say, hey, these have been up here 10, 15 years now. Amade knows all about this. This is a good opportunity for us to upgrade to new inverters and panels, which we can do at a much cheaper cost than we put it on initially, because the wiring is staying the same, it's not changing, and we can just reuse the original racking.
All right.
One other question there, Liam. You talked about the angle a little bit, but I didn't hear an actual preferred angle at this latitude.
I believe it's 22 degrees. Okay. I'd have to double check that, but it's the thing too is even if you're only, let's say, 10 degrees either way, the amount of difference that makes on an annual basis is only like a couple of percentage, if that. So it's generally, if you're able to build from scratch and get the perfect angle, that's fantastic. But if you don't have that, it's not generally worth the extra cost of, I should be 10 degrees more than it is, so now I'm gonna build out some fancy racking for the roof. Instead of that, just use the roof as your angle, and then even if it's 1-2% less per year, it doesn't make that much of a difference. Especially now, because in the past, the solar panels, in terms of the amount of wattage they produced, wasn't a lot. So you really wanted to try to squeeze the most amount that you could in terms of, okay, I really want to be on the self-facing and get the perfect angle, because the panels then were, even 7-8 years ago, the panels were 275 watts. Now they're 450 and up, just in 7 years. So we're able to, and for the same size. So because of that, we're able to put them in places we wouldn't have before, or the fact that the fact that your angle is a little bit off really doesn't make that as much of a difference, just because the wattage is so much higher.
I just want to make a comment. Coming next, when we get into the paybacks, I actually have a graph that shows if it faces north, south, east, west, what happens when you change the angles and that kind of stuff. So that detail is coming next week.
Perfect. Thanks, Jerry.
I have a big voice.
Okay.
Can you use solar panels? Can you use solar panels as a roof on a deck, or do you need a membrane or something underneath, or can you use actual panels?
You can definitely use the solar, especially if you're covering a deck. You can definitely use the solar panels as a roof, because there is a bit of expansion and contraction as they heat up and cool down of the solar panels. You can't use it as like a watertight roof for your house, but if it's, I'd like to mostly cover my deck, you sort of have a couple of options. One is, I want to mostly cover it, and if there's a little bit of water that gets in it seeps through in a couple of places, I don't care. You could just put the panels right on top of the racking, or you could put some very simple sort of membrane down underneath that's just directing whatever water off of the solar panels, and kind of use the racking as an awning itself. Right, thank you.
Well, thank you so much, panel. That was fantastic. I know we're going to roll up our sleeves next week and learn about a whole bunch of other things, including how we can pay for all of this. There's so many programs, and they're going to walk us through what they are and how we can decrease those payback times even more. This kind of geeky goodness is just like, it's so wonderful, and I really appreciate all the detail and how you've kind of made it understandable, and I know that you're great resources for people that are trying to do this. I want to have you join me in thanking 3 really important sponsors that have made this speaker series and this night happen. And next week, the Blue Act Marine Society for organizing this entire thing, the Sunshine Coast Credit Union, and the town of Gibsons have all co-sponsored this series, and we thank them very much. There's a panel at the back by the Sunshine Coast Credit Union, and they've got some eco-home loans that they're talking about there. So that's just one of the many incentives that we're going to be addressing next week. So please join us again the exact same time, the same place, next Wednesday. Thank you very much for coming.